Chapter 3. Okay, chapter 3 is a whole chapter all to itself. It's not split up into two parts like sometimes they are. So we're going to do all of chapter 3. We're going to do 3-1 today. 3-2 the next 2 days, review and have a quiz on 3-1 and 3-2. Then we do 3-3, 3-4, 3-5, and then we take a test. So it's 5 sections long. And we're going to learn how to find the derivative of pretty much all the things. It's very exciting. So calculus has really two branches. There's derivatives and there's integrals. And they're actually opposites of one another pretty much. All right, so here we go, 3.1. All of 3.1 today. The reason why we're doing all of 3.1 is because it's kind of a lot like chapter 2. Derivatives. Well, we're going to learn how to find the derivative of any function and non-functions too. So, let's do this first part. Here we go. First thing, letter A. All right, here's what the derivative is. The derivative. You've already done it, which is exciting. The derivative is, it looks like this, f prime of x. So if we have a function and we want to find the derivative of it, the derivative is called f prime of x. Some people call it also y prime. Y prime. Another way to write it would be dy dx. And it's very exciting because calculus was actually invented by two people in different parts of the world at the exact same time. Wow. Newton and Leibniz. Yeah, and there's this big war, and Newton was a jerk. You know that? I know. He was a really terrible person. Yes, I do. I'll show you in my history of mathematics book.
They were exactly the same.
Yeah.
That's cool, actually.
I know, right? Look at. Let me pause this real quick. Is the derivative then? Well, the derivative, f prime of x, is equal to, and you're going to just like freak out here. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. Have you seen that before? The entire chapter 2 was based around that. That's called the derivative. And I didn't call it the derivative, but, you know, it is the derivative. And basically what that is that helps to find the slope of the tangent at a point. At a point. And that's all the derivative is. The derivative is the rate of change at any point on a graph. So for example, if I said, let's do number 1. And we did we're given this cubic function. F of x equals x cubed. Okay? And we have to find the derivative of that. You have to find f prime of x. Okay, you would have to then plug that into that whole thing. We did that. We did x plus cubed one time. Remember we did the binomial expansion theorem? 1, 3, 3, 1, and then we got all the stuff. And it ended up being that we got 3x squared at the end. And I'm going to teach you a shortcut later on in this chapter about that. And then what the question was to find the slope at x equals 2. Okay, and it helped us find the rate of change at exactly 1 point at x equals 2. And so you plug in 2, and you get that the slope is 12. Trevor, did you turn this to freezing when you walked in?
Maybe.
Yes, it's freezing in here.
It was nice.
Oh, okay, you're good. Oh, okay. All right, now, nobody really wants to take x plus h and cube it, right? That's pretty bad. No, I mean, you can't. It's pretty easy, though, if you knew the binomial expansion theorem to go 1, 3, 3, 1, and do the whole thing. But there's actually an alternate definition of a derivative at a point. Okay, so here it is. You have to know this. So the alternate definition at x equals a. So if they tell me that I need to find the derivative, or the slope, at x equals 2, then I can use this alternate definition, which says f prime of a is equal to the limit as x goes to a for f of x minus f of a all over x minus a. Okay? And I'm going to show you with that last problem how this works. So if you were to take, let's use the alternate definition on that last problem. So number 2, use the alternate definition to show that f prime of x is 3x squared if f of x is x cubed. Okay? We're going to use it just to show that the slope is 12, really. So here we go. Let's use that alternate definition. Let's use it just with a for now. Let's just say at x equals a. Now, let's not make it 2 yet, because I want to show you how to do that too. So let's do f prime of a is equal to the limit as x goes to a. Okay, so here we go. We're going to do f of x. Well, what is f of x? We're using this alternate definition right here. What is f of x? F of x is x cubed minus f of a. What's f of a? A cubed over x minus a. Now, if you were to take a and plug that in, you would get 0 over 0. So there's actually something that you can do here, algebraically. Do you remember how to factor the difference of 2 perfect cubes? No? That's one of those that everyone forgets. It's x minus a, so it's the cube root of x minus the cube root of a, x squared, plus ax plus a squared. You're like, nope, forgot how to do that. Yeah, that's the factorization of the difference of 2 perfect cubes. And then what happens is the x minus a is reduced. Okay? And now let's take the limit as x goes to a. So we're going to plug in a for all the x's that we see. So I get a squared plus a times a plus a squared. So I have a squared plus a squared plus a squared gives me how many a squares? 3a squared. Yeah, it's the same thing, right? Just at x equals a instead. We could have plugged in 2 at that point.
There's another shortcut.
Yeah, there is. There's a
Wasn't Katie showing us?
big time shortcut coming up.
Katie was showing us.
All right, number 3. Use the alternate definition. Use the alternate definition. Given f of x equals the square root of x to find f prime of x. Use the alternate definition to find f prime of x. Just at x equals a. Not at a specific, x is 9 or 4 or whatever. Just at x equals a. Okay. Here we go. We're going to plug it in. Here's the alternate definition. The limit as x goes to a. It's a whole nother one to memorize. So we get f of x, which is the square root of x, minus f of a, which is the square root of a, over x minus a. It's much simpler, though, right, than f of x plus h minus f of x all over h. I think it's a little simpler. So for this one, if you plug in a right away, you'll get 0 over 0. Okay, so we need to do some algebra to fix that. So let's multiply top and bottom by what? Conjugate, yes. Rad x plus rad a. Megan, you get out at 10:15 today? Rad x plus rad a. Where are you at? Oh, you're right there. Okay. Lucky. Take us all with you. Okay, so we got to multiply by the conjugate. So we're going to go limit as x goes to a, and let's FOIL the numerator. So rad x times rad x is x. Outside, inside cancel out. Negative rad a times rad a is minus a. Ooh, that's exciting, isn't it? Okay, thanks. Rad x plus rad a. All right, so now these reduce. Don't forget to put a 1 up top. when you reduce them. And now take a and plug it in for x. So you get 1 over rad a plus rad a, which is 1 over 2 rad a. It's funny because once you get to calculus, no one cares about rationalizing anymore. It's lit. Is it high-key dummy lit? No? No? Okay. Really? Thomas? I thought I sounded like Johnny. Shout out to Johnny. All right. Now, I think I'm supposed to do this one. I am. This one's a tough one. Are you ready? This is the last one. No. I know, right? When does the shortcut come into
Now that I'm
effect?
looking at it, the shortcut makes sense.
It's so good, right?
It takes 2 seconds and you're done.
I don't even think the shortcuts
No, why
today
doesn't
or
the
tomorrow.
shortcut work?
I think the shortcut doesn't happen till next Monday.
I literally
Something to
not
look forward to,
explain
though.
it to Katie's, but the shortcut.
All right, it's number, what are we on, 4? Last one. It's a lot different than the ones we've seen. So don't quit on me. Don't think you've learned it all. You haven't. Here we go. I'm going to give you a graph of a function. -2, put a dot there. I'm going to put a dot there. 1, 2, 3, 4, 5. And then this will be -1. Okay, and then put a dot at 2, -1. And then we'll put a dot over here at 5. Okay, and we'll connect the dots. There and there. All right, so very simple, basic graph. Just a bunch of line segments put together. It's a piecewise function, but I'm not going to make you, give me what the piecewise function is. This is what we're going to do. We're going to graph the derivative of this function. So we're going to call this function y equals f of x, and we're going to graph the derivative y equals f prime of x. Okay? So here we go. Now, the derivative, if you remember, is the slope of the tangent. Okay? It's the slope of the rate of change during those points. Now, if you take a look at this, when x is from -2 to 0, this part right here, that part right there has a specific slope from -2 to 0. What is the slope of that part? Right there. You would rise 1 and run 2. 1/2. Perfect. That is the derivative of the function from -2 to 0. You got to remember, the derivative is the slope. Okay? Slope of the tangent. This slope is constant because it's a line. Now, yes. Well, there's going to be one derivative, but multiple parts of the graph. Now let's look at the next part. X is from 0 to 2. So this part right here. Is it 1? It's down 2 over 2, so it's -1, right? So the slope is -1. Okay. And then finally we have the last part, which is when x is from 2 to 5. And what's the derivative of this function from 2 to 5? 0. Okay. So now what I'm going to do is I'm going to graph the derivative. I'm going to graph all of this. So draw a graph. And here's what the derivative looks like. X is from -2 to 0. The slope is 1/2. So what I'm going to do is I'm going to go from -2 to 0. The slope is 1/2 there. Okay, so what I'm graphing is this is x, and this is f prime of x. It's very strange to this is not x and y anymore. It's the graph of x with respect to f prime. Have you done this in physics when you graphed the velocity? No. Okay. Yes? Someone said yes? Yeah? Okay, now let's graph. So that's the blue part. I probably should have graphed that in blue.
Oh, the velocity graph.
Yes, the velocity graphs.
It's the same.
Okay, and then the next part is from 0 to 2, the derivative, or the y value, which is f prime of x, is -1. So you go to -1, put an open circle, open circle.
Where is it? Why is it open circle?
Okay, it's open circle because, see the blue part? It's changing, the slope's changing from 1/2 to 0. So if you look up here, at this point right here, what is the slope there? Is it 1/2? Or not 0, I'm sorry. Is it 1/2 or is it -1? It's neither, okay? There's no derivative at that point. Because which one is it? It's different on this side than it is on that side. It's almost like the derivatives have to be the same.
So why is it a closed circle?
Well, right here, there's nothing on the other side of it. Yeah, so it's just it. Okay, and then let's do the green part. So from 2 to 5, 2, 3, 4, 5, the slope is 0. So open circle here, and it goes like this to 5, and 5 is a closed circle. So the endpoints are closed circle, but where it changes in the middle, at all of those points where it changes, then that's going to be open circles, because there's no derivative there. Okay, and then they'll ask you something like this. Where is f prime of, or where is f of x not differentiable? I can never spell that, differentiable. I'm not sure if that's how you spell it. Where is f of x not differentiable? Differentiable. I didn't say it. Okay, so that would be at all of your open circles on your f prime of x. So that would be at x equals 0 and 2. Is that it? Yeah. 0 and 2. Okay?
So we don't have to do a point for that?
No.